This is SpaceTime Series 25, Episode 83. Coming up on SpaceTime, 3 new particles discovered at CERN, a new telescope to test competing theories of dark energy, and Cygnus used to boost the International Space Station for the first time. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
The international LHCb collaboration at CERN's Large Hadron Collider has discovered 3 new never-before-seen subatomic particles. These include a new kind of pentaquark and the first ever pair of tetraquarks, which includes a new type of tetraquark. The findings add 3 new exotic members to the growing list of new hadrons found by the world's largest atom smasher. They'll help physicists better understand how quarks bind together into these composite particles. Quarks are elementary particles in the Standard Model of Particle Physics, the cornerstone of science's understanding of the universe. They come in 6 different types or flavors: up, down, charm, strange, top and bottom, sometimes called beauty. They usually combine together in groups of 2s and 3s to form hadrons, best known of which are the protons and neutrons that make up the atomic nuclei. More rarely, however, they also combine into 4-quark and 5-quark particles known as tetraquarks and pentaquarks. These more exotic hadrons were predicted by theorists at the same time as conventional hadrons, which is about 6 decades ago, but they've only relatively recently, that is within the last 20 years or so, been observed by the LHCb and other experiments. Most of the exotic hadrons discovered over the past 2 decades are tetraquarks or pentaquarks containing a charm quark and a charm antiquark, with the remaining 2 or 3 quarks being up, down or strange, or one of their antiquark counterparts. But in the past 2 years, LHCb has discovered different kinds of exotic hadrons. 2 years ago, the collaboration discovered a tetraquark made up of 2 charm quarks and 2 charm antiquarks, and 2 open charm tetraquarks consisting of a charm antiquark, an up quark, a down quark, and a strange antiquark. And then last year, they found the first ever instance of a double open charm tetraquark with 2 charm quarks and an up and down antiquark. Open charm means the particles contain a charm quark without an equivalent antiquark counterpart. The new discoveries include new kinds of exotic hadrons. The first kind, discovered in an analysis of decays of negatively charged B or bottom mesons, is a pentaquark made up of a charm quark and a charm antiquark and an up, down and strange quark, and this was the first pentaquark found to contain a charm quark. The finding had a most impressive statistical significance of 15 standard deviations, far beyond the 5 standard deviations required to claim a new discovery in particle physics. The second kind is a doubly electrically charged tetraquark. It's an open charm tetraquark, composed of a charm quark, a strange antiquark, and an up quark and a down antiquark. And it was spotted together with its neutral counterpart in a joint analysis of decays of positively charged and neutral B mesons. The new tetraquarks were observed with a statistical significance of 6.5 standard deviations for the doubly charged particle and 8 standard deviations for the neutral particle, the first time a pair of tetraquarks have been observed. LHCb physics coordinator Niels Turing says the more analysis being performed, the more kinds of exotic hadrons are being found. He describes it as a period of discovery similar to the 1950s, when the particle zoo of hadrons started being discovered, which ultimately led to the quark model of conventional hadrons in the 1960s. Finding new kinds of tetraquarks and pentaquarks and measuring their properties will help theorists develop a unified model of exotic hadrons, the exact nature of which is currently still largely unknown. It'll also help scientists better understand conventional hadrons. While some theoretical models describe exotic hadrons as single units of highly bound quarks, other models envisage them as pairs of standard hadrons loosely bound in a molecular-like structure. Only more time and study of exotic hadrons will tell if these particles are one, the other, or both. This is SpaceTime. Still to come, a new telescope to test competing theories of dark energy, and the Cygnus cargo ship used to boost the International Space Station up into a higher orbit. All that and more still to come on SpaceTime. Okay, let's take a break from our show for a word from our sponsor, NordVPN. And let's check out their great deal for SpaceTime listeners. Now, if you're not familiar with NordVPN, they're a service that provides online security and privacy. Now, we use them at SpaceTime, and we've been using them before they became a sponsor. And the reason we use them is because they're really good and they work. And there's never been a better time than now for you to take care of your online security as well. Right now, if you subscribe to the NordVPN Complete Security Package, you'll get a massive discount. The package includes 2 years of superior VPN protection, there's malware protection, there's a tracker and an ad blocker, there's the cross-platform password manager NordPass, a data breach scanner, and 1 terabyte of encrypted cloud storage. And of course, it can be loaded onto all your devices. It's an incredible deal, and one which you really should take advantage of. And if you're not impressed with it after giving it a try, you can always get your money back again thanks to Nord's 30-day money-back guarantee. So what have you got to lose? NordVPN's Complete Security Package is just one of a range of packages available from NordVPN, one of which is bound to suit your needs. And all our plans come with an exclusive extra month for free if you use our special URL. So don't miss out on these great offers. Head over now to nordvpn.com/space and sign up today. That URL again for our very special offer is nordvpn.com/space, or use the code Stuart Gary at the checkout. And of course, we'll include those URL details in the show notes and on our website. And now, it's back to our show.
You're listening to SpaceTime. SpaceTime with Stuart Gary.
Simulated tests of the ultra-deep field galaxy survey observations expected from NASA's upcoming Nancy Grace Roman Space Telescope mission have been astounding astronomers. The telescope, planned to launch in 2027 to the Lagrangian L2 halo orbit on the opposite side of the Earth to the Sun, will undertake groundbreaking panoramic surveys of the distant universe, analysing millions of galaxies strewn across space and time. These observations will allow scientists to test different hypotheses to try and explain dark energy, a mysterious force which is causing the expansion of the universe to accelerate. Nancy Grace Roman will explore this mystery using multiple methods, including spectroscopy, the study of the colour information in light. You see, detailed wavelength patterns, called spectra, reveal detailed information about the object that emitted the light, including how fast the object's moving towards or away from us, its chemical composition, and even its temperature. Astronomers call the phenomenon when an object's moving away from our viewpoint as being redshifted. That's because when the object recedes, all the light waves we receive from that object are stretched out and shifted to the red end of the electromagnetic spectrum. Back in the 1920s, astronomers George Lemaitre and Edwin Hubble used redshifts to make the startling discovery that, with very few exceptions, galaxies all seem to be racing away from us and each other, and at different speeds, depending on their distance. By determining how quickly galaxies are receding from us, carried by the relentless expansion of space-time, astronomers can find out how far away they are. The more a galaxy's spectrum is redshifted, the further away it must be. This technique precisely allows astronomers to measure how fast the universe is expanding in different areas, and consequently tracing how the universe has evolved. While designed to explore cosmic acceleration, Nancy Grace Roman will also offer clues about many other tantalizing mysteries. It'll help scientists understand the first generation of galaxies, allow them to map dark matter, a mysterious substance which can only be detected by its gravitational influence on surrounding matter. Nancy Grace Roman will also reveal new information about structures that are much closer to home, right in our own local galactic neighbourhood. The telescope, which is planned for launch in May 2027, will provide such an enormous view of the universe that it will help scientists study cosmic mysteries in an unexpected way. You see, each image will contain precise measurements to so many celestial objects that it will enable statistical studies which simply aren't practical now using telescopes with narrow fields of view. Nancy Grace Roman spectroscopy survey will cover nearly 2,000 square degrees. That's about 5% of the entire sky in just over 7 months. A report in the Astrophysical Journal claims the telescope's survey observations should reveal precise distances to some 10 million galaxies, going back to a time when the universe was just 3 to 6 billion years old. And these measurements will allow astronomers to map the web-like large-scale structure of the cosmos. The survey will also unveil the distances to some 2 million galaxies from even earlier in the universe's history, back to a time when the cosmos was between 2 and 3 billion years old. That's unexplored territory in large-scale cosmic structure. This will allow astronomers to create a three-dimensional map of the universe by measuring accurate distances and positions to millions of galaxies. Learning how galaxy variation varies with distance and therefore time will give astronomers a window into how quickly the universe has expanded in different cosmic eras. The study will also correct galaxy distances using the echoes of sound waves generated just after the Big Bang. These sound waves, more accurately pressure waves, are called baryon acoustic oscillations, and they've grown with time due to the expansion of space, leaving their imprint on the cosmos by influencing galaxy distribution. See, it works like this. For every modern galaxy, you're more likely to find another galaxy around 5 million light years away than what you are likely to find one slightly nearer or further away. That's due to baryon acoustic oscillations. And looking further out into the universe, into earlier cosmic times, means that this preferred physical distance between galaxies, the vestige of baryon acoustic oscillation ripples, decreases. And so through these, we have another measurement of the universe's expansion history. Galaxy redshifts also encode information about their motion due to the gravity of their neighbours. These are known as redshift space distortions, and they help astronomers trace the growth history of large-scale cosmic structures. Learning about how the cosmos has expanded and how structure has grown within it will allow scientists to explore the nature of cosmic acceleration and thereby test Einstein's theory of gravity over the age of the universe. You see, as the universe expands, the gravity of the matter within it should slow down that expansion. So astronomers were surprised to learn that the expansion of the universe was actually speeding up, because it means that something about our picture of the universe is still very wrong and on a cosmic scale. The mystery could be explained by adding a new energy component to the universe, a component which scientists have named dark energy. Or it could indicate that Einstein's theory of gravity, that's his general relativity theory, needs some modification. Now, changing the equations that describe something as fundamental as gravity may seem extreme, but it's been done before. Sir Isaac Newton's law of gravity worked great on a local scale, but it couldn't explain some of the things astronomers were seeing further out in space, such as a small and mysterious discrepancy in Mercury's orbit. Astronomers ultimately found that Einstein's general theory of relativity perfectly accounted for these issues. Switching from Newton's description of gravity to Einstein's involved transforming modern physics by changing the way we view space and time, interconnected instead of separate and constant. Cosmic acceleration could be a sign that Einstein's theory of gravity still isn't quite right. The thing is, general relativity has been extremely well tested on physical scales up to about the size of our solar system, but less so on larger cosmological scales. The simulations from what's expected from the Nancy Grace Roman Space Telescope suggested the mission will provide one of the best opportunities yet to discern between the leading theories that attempt to explain cosmic acceleration. Put simply, the observations will tell astronomers whether cosmic acceleration is caused by dark energy or whether there's a need to modify Einstein's general theory of relativity. This report from NASA TV.
In 2004, NASA's Hubble Space Telescope changed astronomy forever when astronomers revealed the first ultra-deep field image. Created with more than 270 hours of observation over the course of a year, it is our farthest ever visible light image of the universe. This tiny window revealed thousands of galaxies in a seemingly empty patch of sky. We can't see any farther in visible light because the unrelenting expansion of space has stretched galaxies' ultraviolet glow into red light. More distant galaxies are mostly detectable in infrared. That's why, in 2009, Hubble captured an infrared ultra-deep field image that probed even deeper into the same spot. It remains one of the most distant images ever made, and a key source of information about some of the universe's early history. The Nancy Grace Roman Space Telescope will have infrared resolution and capabilities similar to Hubble, but each image will cover 200 times the area of sky. A potential Roman ultra-deep field could be far faster to capture, yet cover hundreds of times as much of the early universe. To further explore this potential, a team of researchers has created a simulated ultra-deep field image. The entire image contains about 1 square degree of sky, or about 5 full moons. Even a single Roman field of view contains a staggering number of distant galaxies, each one filled with billions of stars. This computer-generated image represents the distribution of galaxies that researchers expect to find based on the existing Hubble observations. It will help astronomers determine how best to conduct an actual Roman ultra-deep field and anticipate the measurements and conclusions they might be able to make. Because light travels at a finite speed, distant images are also snapshots earlier in time. Ultra-deep field images reveal a time from about 200 million to 1 billion years after the Big Bang. Roman's image would be the largest observation of its kind for this time period and could reveal key features in the adolescent universe, including rare infant galaxies that eventually evolve into mature galaxies like our own Milky Way. With Roman set to launch by 2027, this simulated ultra-deep field image is just one example of the fantastic results this upcoming mission could bring by the end of the decade.
The Nancy Grace Roman Space Telescope is a sibling of the famous Hubble Space Telescope, and they aren't alone. In fact, since 1976, there have been at least 23 space telescopes, all of which use exactly the same basic design as that adopted for Hubble. But unlike Hubble and Nancy Grace Roman, which point upwards into the heavens, the other 21 telescopes are all used for Earth observation. They're spy satellites built by the National Reconnaissance Office, the United States intelligence agency responsible for space-based surveillance. They've gone by a variety of different official and code names, such as KH-11, Kennen, Crystal, Evolved Enhanced Crystal, 1010, Gambit, and Hexagon, but they're probably best known by the name Keyhole. Over the years, there have been at least 6 basic technology upgrades known as blocks, and at least 2 of them, called Misty, were even designed to be stealthy and virtually invisible to radar. But the story of the Nancy Grace Roman Space Telescope really begins in 2012, when the National Reconnaissance Office donated a pair of Block 3 Keyhole spy satellites and spare parts to NASA, potentially for use as Hubble Space Telescope replacements. The pair were manufactured in the late 1990s and early 2000s, so they were newer than the Hubble. They were originally meant to join the constellation of similar keyhole surveillance and reconnaissance spy satellites orbiting the Earth, but were never used because specific segments of their design were superseded by newer Block 4 and 5 versions. Like Hubble, they were built by Lockheed Martin, equipped with a 2.4-metre main mirror and designed to orbit at altitudes of around 500 kilometres. But because they look down to the Earth's surface and not up, they use different optical equipment. And they also have a shorter focal length, giving them a far wider field of view, around 100 times larger than Hubble's Wide Field Camera 3 instrument. But they won't complete, lacking among other things detectors, star trackers, prism wheels and filters. The good news is they did come complete with bodies, mirrors, payload radiators, and 1.5 meter long struts on the bottom of the spacecraft for instruments. And it's one of these that are now being built into the Nancy Grace Roman Space Telescope. This is SpaceTime. Still to come, Cygnus used for the first time to boost the International Space Station up into a higher orbit. And later in the science report, the latest snapshot of Australia's current attitude towards illegal drugs. All that and more still to come on SpaceTime. NASA has used a docked Northrop Grumman Cygnus cargo ship to boost the International Space Station up into a higher orbit for the first time. Atmospheric drag, even in the space environment 400 kilometers above the Earth, still contains enough molecules to cause the orbiting outpost to continually lose altitude and degrade as it circles the planet. And so it's got to be boosted at regular intervals. During the 301-second burn of the Cygnus NG-17's gimbal delta velocity engine, the space station's altitude was raised by 160 meters in apogee and around 800 meters in perigee. Originally, this was a task assigned to visiting space shuttles. However, when the space shuttle fleet was suddenly retired prematurely in 2001, the Russian Federal Space Agency Roscosmos agreed to take over the job using their visiting Progress cargo ships. The problem is, the growing tensions over Moscow's invasion of the Ukraine has seen all space cooperation between Russia and the West brought to a halt, other than for the jointly operated International Space Station. And while both sides are still cooperating in keeping the space station flying, there was even a spacewalk carried out by a Russian and European astronaut earlier this week. Roscosmos has reacted to Western sanctions by banning cosmonauts from participating in many Western scientific experiments on station, or for that matter, even using Western equipment on the station. Things are so bad, at one stage last month, Roscosmos threatened to stop boosting the space station, to which SpaceX boss Elon Musk simply tweeted a picture of a Dragon capsule with the word ready. Now, while all this was going on, Northrop Grumman had already been quietly carrying out upgrades to the Cygnus cargo ship, increasing payload capacity with larger cargo modules, adding lighter and more powerful solar arrays and fuel tanks, and upgrading many of the spacecraft systems to make a reboost possible. An earlier reboost attempt using Cygnus was aborted after just a few seconds as a precautionary measure. But after adjusting flight limits, another attempt was carried out, this one successfully lifting the space station up into a higher orbit. Just days after the maneuver, a SpaceX Dragon cargo ship loaded with over 2.5 tons of supplies docked successfully to the International Space Station. The CRS25 mission docked automatically to the forward port of the Harmony module 2 days after launching on a Falcon 9 rocket from Pad 39A at the Kennedy Space Center in Florida.
Now, Dragon began its startup sequence at T-minus 35 minutes when it coordinated timing with the Falcon 9. Dragon now currently undergoing vehicle health checks, with the next big step just before liftoff when the cargo spacecraft transitions to internal battery power.
Dragon is in terminal count.
And we just heard that call out for Dragon being in terminal count. And the strong back retract, that's perfect timing. That large truss structure next to the vehicle is called the transporter erector or the strong back. And as was called out on the loops, it pulls away from the vehicle in preparation for liftoff. Those clamp arms around the body of the second stage start to retract. And then shortly after that, the whole structure will pull away from Falcon 9. Now, in these last few minutes, Falcon 9 is performing a set of final health checks on its primary communications, avionics, and propulsion systems in preparation for liftoff. We're also going to continue to hear call-outs throughout that the engines are sufficiently chilled in as we get closer to liftoff.
Checkouts of the second stage thrust vector control actuators. They are underway. This is often referred to as the engine wiggle test. This is when SpaceX moves the thrust nozzles slightly to make sure that the guidance hardware is go for flight. At the time of launch, 8:44 and 22 seconds p.m. Eastern Time, the International Space Station will be over the Pacific Ocean, 257 statute miles in altitude.
Now, we actually heard just about 30 seconds ago that liquid oxygen loading is complete on the first stage. And coming up here, just under 20 seconds, we'll hear a similar call out on the second stage. That will wrap up propellant loading on Falcon 9 in preparation for launch. At this point, Dragon is performing its final health checks to make sure we're ready to go for rendezvous with the space station about 38 hours from now. There's a call out there for LOX load complete.
At T-minus 1 minute, Dragon will transition to internal power. Falcon 9 computers will enter startup mode and begin final pre-launch checks, guiding the rocket through the last seconds before liftoff.
Falcon 9 is in startup.
Here we have the call.
Dragon is in countdown.
Both stages are now pressurizing for launch.
LD is go for Falcon 9, CRS25 launch.
So range is go, weather is go. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Engine ignition. And liftoff. Liftoff of SpaceX's Falcon 9 rocket, launching Dragon on the 25th mission to resupply the International Space Station with cool science and a new advanced instrument to more effectively study our planet's climate.
Power and telemetry nominal.
There's the call out for maximum dynamic pressure. So from here, the stresses on the vehicle will get lower and lower as we raise our altitude. Coming up, we've got 5 events back to back. The first of those will be main engine cutoff, or MECO. That's where all 9 Merlin 1D engines on the first stage will shut down.
I'm back, chill.
Following that will be stage separation, where the first and second stages will separate. The first stage will flip around to make sure it's headed back towards the landing site and our drone ship named a shortfall of gravitas. And then the second stage will ignite its Merlin vacuum engine to boost Dragon into low Earth orbit during second engine start number 1. We just heard the call out there for engine chill-in on the second stage engine starting. The last event is the boost back burn on the first stage. That's to reduce the velocity of that vehicle as we prepare for atmospheric entry. Now, all of those events happen over about 45 seconds.
MECO. Stage separation confirmed. And back startup.
So the first 3 of those events are complete.
Startup.
And now the boost back burn is underway.
Stage 1 boost back shutdown.
Successful shutdown of the first stage Merlin engines for the boost back burn. Second stage engine continuing to burn. That'll continue to burn until about the T+8 minute and a 40-second mark into the mission. Our 30th mission of 2022 and the 3rd Dragon flight to the International Space Station this year. We lifted off just about 4 minutes ago from the Kennedy Space Center in Florida. Now, speaking of the entry sequence on the first stage, to make its way back to that drone ship, it's going to have to execute 2 more burns. The first of those is the entry burn, where we'll ignite 3 of the Merlin engines, and that helps slow down the stage as we enter the upper part of the Earth's atmosphere. Following that, there will be a second burn, the landing burn, and there will only ignite a single Merlin 1D engine that'll bring the vehicle speed down to 0 for a soft touchdown on the drone ship. The plumes of white, that's actually from our nitrogen gas thrusters that are helping to keep the first stage oriented, engines down, as we are in the vacuum of space at the moment. But once we get through that entry burn, the grid fins, which are deployed, will then take over control as we start to get atmospheric authority. And then the first stage will only use those grid fins to steer back towards our drone ship. So entry burn expected to start about 10 seconds for now.
1 FTS is saved.
Just taking a quick look in, stage 2 engine performance, about nominal, continuing to burn. We've got about 3 more minutes for that
Stage 1
burn.
entry burn startup.
The velocity on the first stage rapidly slowing down as we
Stage 1
fire
entry burn shutdown.
the entry burn. That burn only lasting about 15 seconds. And now we're doing a quick attitude correction to make sure we're pointing the heat shield down. And that entry burn and the plume coming back on the stage ends up depositing a small layer of carbon on the vehicle, which is what gives our first stages that awesome sooty look once we've reflown them. The Falcon 9 also has 4 landing legs. They're made of carbon fiber and aluminum honeycomb. They're placed around the base of the rocket, and they'll deploy just prior to landing during the landing burn. If we're successful in recovering this Falcon 9, it'll mark its 5th successful landing and our 130th landing overall of a Falcon 9, including Falcon Heavy missions. So landing burn coming up shortly.
Stage 1 landing burn. Stage 1 landing leg deploy.
People real excited behind me, right in the middle. 5th landing for this Falcon 9, 130th landing overall for an orbital class rocket. Beautiful sight to see. Now coming up next is second engine cutoff number 1, or SECO 1. We'll expect the Merlin vacuum engine to stop firing just about 30 seconds from now. It's carrying the Dragon spacecraft to its drop-off orbit around our planet. After we complete second engine cutoff number 1, we'll do a quick check to make sure that the burn performance is as expected.
Stage 2 MTS.
We're in the targeted orbit. We usually hear that called out as a nominal orbital insertion or a good orbit call out on the loops.
And back shutdown.
So you heard a call out on the loops there for shutdown of the Merlin vacuum. There's nominal orbital insertion. So that means that the ground teams have assessed the orbit, and stage 2 is right where we want it to be. And of course, that also means that Dragon is right where we want it to be, since it's been riding on the the second stage this whole time.
The flight's primary payload was Emmet, the Earth's surface mineral dust source investigation spectrograph developed by NASA's Jet Propulsion Laboratory, which we covered in last week's show. Emmet will be mounted on the outside of the space station, from where it'll measure the composition of dust in the Earth's atmosphere and determine where the dust is mostly coming from and where it's blowing to. The mission's also transporting a new main bus switching unit, which will replace a degraded one on the space station's S6 truss. Also aboard the Dragon were 2 new NASA spacesuits. They'll replace the older suits, one of which has started to show its age, leaking water during recent spacewalks. The CRS25 manifest also includes an experiment using tissue chips in order to study how microgravity affects the human immune system during spaceflight. There's also a soil experiment designed to determine how microgravity affects complex communities of microorganisms as they carry out key functions in soil, including the recycling of carbon and other nutrients and supporting plant growth. The Genes in Space 9 experiment will test free production of protein in microgravity and evaluate 2 cell-free biosensors that can detect specific target molecules. This will ultimately provide a simple, portable and low-cost tool for medical diagnostics, on-demand production of medicines and vaccines, and environmental monitoring on future space missions. Another experiment will look at the process of creating concrete alternatives in space, using a mixture of organic and on-site materials, such as lunar or Martian dust. The mission also carried 6 CubeSats, including the Beaver Cube, which was built by American high school students and equipped with 1 visible and 2 infrared images to measure cloud properties, ocean surface temperatures and ocean color in order to study the Earth's climate and weather systems. Just 2 days after the Dragon launch, SpaceX launched another Falcon 9, this one from the neighbouring Launch Complex 40. It was carrying another 53 Starlink broadband internet satellites into orbit. The flight marked the 13th launch for the same Falcon 9 booster, which then successfully returned to Earth, landing on the drone ship Just Read the Instructions, which had been pre-positioned about 650 kilometres downrange northeast of Cape Canaveral in the North Atlantic Ocean. That mission means SpaceX have now launched an incredible 2,858 of the 260 kilogram Starlink satellites. They eventually hope to get that number up to around 30,000. This is SpaceTime. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favorite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.